This is a review for Math 1060, Exam 1. The review is going to touch on most topics we've covered in the class so far. For extra practice, you may want to check out the worksheets that are posted in the Canvas modules, look over problems that we've done in class, and rework some of the problems on your quizzes and online homework. For now, let's get started with a few problems that will hopefully remind you of some things that we've looked at earlier in the semester. Starting with the first problem that we'll do here. And keep in mind, most of these problems should be completed without a calculator. And for most of these problems, your answer will be in radians. In fact, unless it's very obvious that your answer should be in degrees, you'll want to use radians for these problems. Okay, so first of all, given that tangent of theta equals -1/2 and sine theta is greater than 0, find the exact values of the remaining trigonometric functions. Okay, so I'm going to look first of all at what quadrant we would be in if the tangent is negative and the sine is positive. And if you think for just a minute about that, that's going to be quadrant 2 here. So we'll be in quadrant 2 where the tangent is negative and the sine is positive. And in quadrant 2, I'm going to throw just some made-up angle up here in quadrant 2. Oh, maybe like so. I don't really care if I have the sides correct lengths or anywhere near that. We're going to call this a reference triangle, though, for this particular situation. And if the tangent is equal to -1/2, for my reference triangle, that means I'm going to have an opposite side of 1 over an adjacent side of 2. The remaining side here, which we could think of as being r for this problem, we would see that 1 squared plus 2 squared equals r squared. And that would give us that r squared is equal to 5, or that r would be equal to plus or minus the square root of 5. Of course, when we're talking about the length of the hypotenuse of a right triangle, that's always going to be positive. So we're going to have r is equal to positive square root 5. From that, we can go ahead and find the remaining trigonometric functions. Well, really, the only function that we have so far is the tangent. So let's figure out what the sine of that angle would be that gives us a tangent of -1/2 and has a side greater than 0. The sine of this angle would be equal to, in quadrant 2, positive opposite over hypotenuse, which would be 1 over square root 5. The cosine, we're in quadrant 2, remember, so the cosine is negative. The cosine would be adjacent over hypotenuse, or -2 over square root 5. From that, we have the tangent. We'll find the cosecant. The cosecant of the angle would be the reciprocal of the sine, which would be square root 5. The secant, the reciprocal of the cosine function, would be negative square root 5 over 2. And the cotangent would be the reciprocal of the tangent function, or -2. Okay, so if you want to rationalize denominators here, you can. You don't have to. Just for practice, let's say we want to rationalize the sine function, the value of the sine function, 1 over square root 5. We would multiply by square root of 5 over square root 5 to give us a result of square root 5 over 5. Okay, so these trigonometric function values can be written in either rationalized form or non-rationalized form. It's pretty much up to you. Let's look at the next problem that we have here. And this is the first of 3 problems in a row that we're going to do without a calculator. And our objective here is to find the exact values of the expression. If the expression is undefined, we want to explain why it is undefined. And generally, that would be when we end up with a 0 in the denominator. We would have an undefined function. For the cosecant of 5 pi over 6, I'm going to start by writing this as 1 over the sine of 5 pi over 6. And then once I figure out what the sine of 5 pi over 6 is, I should be good. Well, the sine of 5 pi over 6, I always look first at what quadrant we're in. 5 pi over 6 would be in quadrant 2 here. And so in quadrant 2, the sine is positive. The reference angle here would be pi over 6 if we have an angle of 5 pi over 6. So the sine of 5 pi over 6 is going to be the same as positive the sine of our reference angle pi over 6. Remember that the sine of pi over 6 is 1/2. We have 1 over 1/2. 1 divided by 1/2 is the same as 1 times 2 over 1. We end up with the cosecant of 5 pi over 6 is equal to 2. Okay, and now we move on to the cotangent of 4 pi over 3. For the cotangent or the tangent, I would write this in terms of sines and cosines. The cotangent of 4 pi over 3 then would be the cosine of 4 pi over 3 divided by the sine of 4 pi over 3. To break this down further, well, let's see, where is 4 pi over 3? It's going to be in quadrant 3 here. So we're in quadrant 3. And in quadrant 3, we're going to have a reference angle of pi thirds. So let's move on to write the cosine of 4 pi over 3. In quadrant 3, both the sine and the cosine are negative. So we're going to have negative cosine of the reference angle of pi thirds over negative sine of the reference angle pi thirds. So we're going to have negative, the cosine of pi thirds is 1/2. The sine of pi thirds is square root of 3 over 2. We can simplify as, whoops, that should be negative over negative, which ends up being positive. Okay, so we can simplify as 1/2 divided by square root of 3 over 2 is the same as 1/2 times 2 over square root 3, and we end up with 1 over square root 3. Again, you can simplify or you can rationalize, I guess I would say, if you like. I don't know that actually a rationalized answer would be simpler. I think maybe the simplest is just to leave it as 1 over square root 3, but it's up to you. Okay, moving on. We have, this time, we have an angle in degrees, so we would want to put our answer in degrees. And so we're looking to find the cosine of 150 degrees. Where is that thing at? Well, we're going to be in quadrant 2 here for 150 degrees. If we went all the way around to the negative x-axis, that would take us through an angle of 180 degrees. So we can see the reference angle here will be 30 degrees. In quadrant 2, the cosine is negative. So we find the cosine of 150 degrees by taking the negative of the cosine of the reference angle of 30 degrees. The cosine of 30 degrees is square root 3 over 2. And that would be our answer then, negative square root 3 over 2. Okay, we move on to problem number 3 here, where we want to find all real numbers that satisfy the equation sine theta equals a negative 1/2. Where I would start at is looking for what quadrants we're going to be dealing with here. So in which quadrants is the sign negative? Well, if you remember, all students take calculus. The sign is positive in the first quadrant and the second quadrant. In the third quadrant, the sign is negative. In the fourth quadrant, the sign is negative. So with sine of theta being equal to negative 1/2, we're going to have a reference angle of pi over 6 in the third quadrant and in the fourth quadrant. That would give us two different angles between 0 and 2 pi, the first being 7 pi over 6, with having a reference angle of pi over 6. The second angle then would be 11 pi over 6. My answer is to find all real numbers that satisfy this equation. So the first thing I'm going to look at is saying, well, one answer here is that theta would be equal to 7 pi over 6. And from that angle, I need to add the fact that I can spin around another 2 pi radians in either direction. So I need to not only say that theta equals 7 pi over 6, but that theta equals 7 pi over 6 plus 2 pi k. And then to include our other angle of 11 pi over 6, I would also say, or theta equals 11 pi over 6 plus 2 pi k. The major work that you need to show for this problem is to sketch a little coordinate system here. And then the other thing that you need to make sure you add is that for any integer k. Okay, and we're done. The answer here is almost longer than the work that you did in solving it. And let's move on. Problem number 4 is to prove that the equation 1 plus tangent theta squared over secant theta is equal to secant theta plus 2 sine theta. We want to prove that this equation is an identity. To prove that the equation is an identity, we can start with either the left side or the right side of the equation. I'm going to choose here to start with the left side of the equation. And so the very first thing I do is I write down 1 plus tangent theta squared over secant theta. The first step in getting this problem correct is to show the left-hand side, show what it is. And then I move on to saying that this is equal to, well, 1 plus tangent theta squared. Notice way off to the side, what we're really doing here is we're taking 1 plus tangent theta times 1 plus tangent theta. And just to remind us what 1 plus tangent theta squared is equivalent to there, and if we want to expand, you could think of foiling these, I guess. You would have 1 plus tangent theta plus tangent theta. So we would have 1 plus 2 tangent theta plus tangent squared theta. And then this is all over the secant of theta. Okay, so I'm going to do a little more work off to the side here, something that I might not include in the work that I'm showing for the problem. So let's say we've got some little scratch paper over here we want to use. The other thing I want to remind myself of is I see I have 1 plus tangent squared theta. In fact, let's go ahead and put 1 plus tangent squared theta. And then put the plus 2 tangent theta all over secant theta, so that we're ready for when I figure out what I want to replace 1 plus tangent squared theta with. Well, you might just remember this, but if you don't, we start with the Pythagorean identities, sine squared theta plus cosine squared theta equals 1. And then I want to get the tangent out of this somehow, so I'm going to divide everything through, or I'm going to divide both sides of the equation through by cosine squared theta. Okay, once we do that, we can see that we have tangent squared theta plus 1 equals secant squared theta. If instead we were trying to get to where we had the cotangent squared, I would divide through by sine squared on both sides of the equation. Okay, but we can see we're aiming for 1 plus tangent squared theta. Now from the Pythagorean identity, we can see that this is actually equal to secant squared theta. So I'll just replace the 1 plus tangent squared theta with secant squared theta. And then just taking a quick peek at the right-hand side here, that is my goal to get to the right-hand side. I can see that I'm almost there with part of this. I can break up my expression here into secant squared theta over secant theta plus 2 tangent theta over secant theta. And if I simplify secant squared theta over secant theta, I'll just rewrite that as secant theta almost there. We got one more step or two. And I can see the next step, if I want to turn, so I have secant theta. If I want to turn tangent theta over secant theta into sine theta, what I want to do here is I want to write tangent and secant in terms of sines and cosines. Whoops, sorry about that. Okay, so we have secant theta plus 2 times tangent theta is sine theta over cosine theta. And then secant of theta is 1 over cosine theta. So we end up with secant theta plus 2 times sine theta over cosine theta divided by 1 over cosine theta is the same as sine over cosine times cosine over 1. We end up with sine theta. Okay, so we actually have the right-hand side here now. We have arrived at secant theta plus 2 sine theta, and we're finished. Okay, moving on. Find the missing sides of the triangle and give exact values. So this is number 5 in our review. So I think I'll start with J, being that J comes before K in the alphabet. And so to find what J is equal to here, well, I can see that I have the opposite and the hypotenuse that I'm working with, which tells me I probably want to use the sine of 30 degrees. And the sine of 30 degrees for this right triangle would be 20 over J, opposite over hypotenuse. Multiplying by both sides by J, I have J times sine 30 degrees equals 20. Then dividing through by sine of 30 degrees, we get J equals 20 over sine of 30 degrees, which is 20 over 1/2. 20 divided by 1/2 is 20 times 2 over 1, and we end up with J equals 40. All right, for K, and looking at the 30-degree angle, I have adjacent and hypotenuse. And so the cosine is what we'll use here. The cosine of 30 degrees equals K over 20. Okay, I think I said that wrong. So the cosine of 30 degrees, we don't want to use cosine here, do we? We want to use actually tangent. Okay, I need to make at least one mistake today, right? And usually it's more than one. So this is at least the first. Okay, so let's look back again. So the opposite and adjacent, we're going to be using the tangent function. So the tangent of 30 degrees equals 20 over K. Multiplying both sides by K, we get K times tangent 30 degrees equals 20. And so K is going to equal 20 over tangent of 30 degrees. Then we remember that tangent of 30 degrees is 1 over square root 3. 20 divided by 1 over square root 3 is the same as 20 times square root of 3 over 1. Our answer is K equals 20 square root 3. All right, so let's move on to our next problem here, which is to sketch y equals 3 cosine of pi x minus pi over 2. And I think I'll actually start here by simplifying a bit. So I'm going to write y as being equal to 3 cosine of, this would be pi x over 2 minus pi over 2 plus 1. And one more simplification, we have y equals 3 cosine, and then I'm going to factor out pi halves from the pi x over 2 and the pi halves that I have. So that's going to leave me with pi halves times x minus 1 and then plus 1. So what have we got going on here as far as transformations? Well, let's see. I like to start with a period. So the period here, and let's make this just a little bit darker. We'll change colors. The period is going to be 2 pi divided by this number in front of the x minus 1, which is pi halves. 2 pi divided by pi halves is the same as 2 pi times 2 over pi, which is going to end up giving us 4. So we have a period of 4 for this problem. And the next thing I'll look at is if I think of y equals 3 cosine of pi halves times x minus 1. Well, actually, if we just started at this step right here, I'm going to think of y as being equal to 3 cosine of omega x minus phi plus b. And I'm trying to write variables there rather than the actual value. So I'm thinking of this is y equals a times the cosine of omega x minus phi plus b. Okay, so we found the period is 4. And the period is omega here was pi halves. We get the period from that pi halves. Then to find what the amplitude is here, the amplitude is going to be the absolute value of A. In this case, the absolute value of A is the absolute value of 3, which is just 3. So we have an amplitude of 3. The next thing we might look for is the phase shift. So the phase shift is going to be the number here. So if we're just graphing like x minus 1 squared or something, we would take the graph of x squared and we would move it to the right 1 unit. So the x minus 1 here, once I factored out the pi halves, tells me that my phase shift is going to be to the right by 1 unit. Okay, so phase shift right 1 unit. And the last thing before we start actually working on the graph itself, what we call the midline, it comes from B. So the midline comes from this value B, which in this case is going to be plus 1. And I'm just going to say in this case B equals 1. Our midline is 1 here. Okay, so how do we graph this thing? Well, if you remember the cosine function generally, we would start at 0. We would go up to 2 pi. And if we divide our graph into quarter marks for the cosine function, we start high. We go on to the midline. For our second quarter mark, we go below the midline, on the midline, and up high again. So we go high, midline, low, midline, high. This would be the graph of the cosine function. Instead of going from 0 to 2 pi, however, for this graph, we are going from... We have a period of 4, so if we were starting at 0, we'd go from 0 to 4 period-wise. However, we have a phase shift, which is to the right 1 unit. So we move everything from 0 to 4 to the right by 1 unit, meaning we're going to start at 1 and we're going to go to 5. Okay, so I think we've got everything we need to graph. I'm going to start by putting on the quarter marks that I get from looking at the fact that our fundamental cycle of this function is going to go from 1 to 5. So we'll put our first quarter mark at x equals 1. Our last quarter mark is at x equals 5. Our middle quarter mark, you can see, is going to be right in the middle here at x equals 3. And then again, we'll split twice more to have a quarter mark at 2 and a quarter mark at 4. Okay, so once I have the quarter marks on, the next thing I'm going to do is the midline, which I tend to do in red just to remind me what I'm doing there. So the midline here, b equals 1, is essentially y equals 1. It brings everything up by 1 unit from the x-axis. So here is the midline. This would be, if you thought about it line-wise, would be the line y equals 1. We use a dashed mark there. And then we'll go ahead and start graphing. So we notice for our amplitude is 3. And we notice that we don't flip the graph here. If this was -3 out in front, we would be flipping our graph about the baseline or about the midline, but there's no flipping going on here. So we're going to follow the pattern that we have going from 0 to 2 pi for the cosine function. We start out high for this function. And so in talking about high and having an amplitude of 3, we're not going up by 1 unit, but with an amplitude of 3, we actually go up 3 units from that baseline, from the midline for our first point. Our second point at the second quarter mark is going to be right on the midline. Our third point will be 3 units below the midline, 1, 2, 3, about right here. The fourth quarter mark will be on the midline again, and the fifth quarter mark will be, in this case, 3 units above the midline, about right here. So we're going to go ahead and graph the function. Whoa, it's a little bit hard to make good lines and curves here with the angle I have to sketch this at. So I'm doing my best here. But notice we don't actually stop right here. We keep going. So to the right, we continue on. And to the left, I can see if I went over 1 unit, I'd be back on the midline about right here. And then I'd drop down again to going another unit to the left. I drop down to 2 units below the x-axis. We'd bounce up again, and we'd keep going like so. So I would go ahead, if you're sketching a graph on an exam, go ahead and sketch the whole thing for that to cover the graph that's shown there. All right, so let's move on. And next we're graphing y equals the tangent of x plus pi halves. And so there isn't too much stuff going on here from the tangent function. I think easiest here would probably be to just start with the tangent function. Let's see if we can remember what that looks like. If I'm graphing y equals the tangent of x, this tangent function has a period of pi. We ordinarily would start at negative pi halves, go to pi. We'd graph a fundamental cycle from negative pi halves to pi halves with a period of pi. We'd put at negative pi halves and at pi halves, we're going to have vertical asymptotes. And then I like to go ahead and put and plot at 1 and -1 for y values on our graph. We're going to have a point that is pi fourths 1, and a point on our graph that is negative pi fourths -1. We would also have the point 0, 0, and then what we're going to do to sketch this, we're going to try to approach those vertical asymptotes, come down, make a smooth curve through all our points, and like so. So this is what the fundamental cycle of the tangent function would look like. All we're really doing here is, if you look at what we're trying to sketch, the only thing that's different than y equals tangent of x is that we have x plus pi halves here in parentheses. So for x plus pi halves, that tells me what I want to do is I want to take the graph of the tangent function and I want to shift to do a horizontal shift to the left by pi halves units. So horizontal shift left by pi halves units. Okay, and keep in mind for the tangent and cotangent function, our period is pi. It's not 2 pi. So let's just look real quickly back at the problem we just did for the problem that we were graphing before. We had a coefficient on the x of pi halves, which meant to find the period, we took 2 pi and divided by that pi halves. With a tangent function, if we were graphing the tangent here, we would divide pi by pi halves, not 2 pi. So keep that in mind. Where the period is quite different is with the tangent and cotangent function. For both those functions, we only have a period of pi. So if there's any adjustment to the period, we're going to divide pi by the coefficient on the x here, rather than dividing 2 pi by the coefficient on the x. So let's do it. Let's move everything left by pi halves units, starting with, I'll move this first vertical asymptote at x equals negative pi halves left by pi half units to put it at negative pi. And I will move the vertical asymptote x equals pi halves to the left by pi halves units, putting it at x equals 0. Okay, so if we just start by graphing this fundamental cycle, right in the middle, we're going to be on the x-axis. At negative pi fourths, we would be at y equals 1. At negative 3 pi over 4, we would be at y equals negative 1. And let's just try to make a nice little smooth curve here. That doesn't look too good. Oh, let me try that one again. Okay. Well, that's a little better. I don't know. Okay, let's go ahead and complete the graph here, going from negative 2 pi to 2 pi. Notice that every pi units, we have another vertical asymptote. So we'll have one at negative 2 pi. We'll have a vertical asymptote at x equals pi and at x equals 2 pi. And so let's kind of repeat our graph here at each of these places, between each of the vertical asymptotes, each pair of vertical asymptotes. Okay. There we go, we got it. Okay, so let's move on. Next thing is to graph y equals cosecant x. So we're not doing any shifting or anything. What I really want to show you here is that whenever I want to graph the cosecant function, I'm going to start by graphing the sine function. And same thing, if I was graphing the secant function, I would start by graphing the sine function. In fact, if I was doing a transformation of the cosecant function, I would first do the transformation on the sine function and bounce off that graph, just like I'll do here. So let's graph the sine function. We have 0, 0. We have pi halves 1. We have pi 0. We have 3 pi halves negative 1. We have 2 pi 0. And if I go to the left here, then I'm going to have negative pi halves negative 1, negative pi 0, negative 3 pi halves 1, and negative 2 pi 0. So I'm going to just do a dotted line here, or I guess a dashed line, to connect these dots for the sine function. Then it's very easy to graph the cosecant function. Okay, so we have y equals sine x right here. And from that, to graph the cosecant function, let's see what we're going to do here. Let's make a different color. We'll do red. Red stands out well. So remember, the cosecant of x is equal to 1 over the sine x. And so the first thing I'm going to note is that whenever the sine is 0, the cosecant is undefined. So at any point on this graph where I have a sine of 0, I'm going to have a vertical asymptote. All right, and then also some other points that I can easily grab here. When the sine is equal to 1, the cosecant would be 1 over 1 or 1. So whenever we have a high point on the sine graph, we're actually going to have a low point on the cosecant graph. But we'll have the same point will be on both the graph of the sine and the cosecant at the high points on the sine graph. And this would work as well if you had a transformation of the cosecant function. You could go ahead and graph that transformation of the sine function, and then you could put your vertical asymptotes wherever your sine graph met the midline, and you could put wherever you have a high point on the sine graph, you would also have that point on the cosecant graph. When we have a low point on the sine graph, sine would be -1 in this case. 1 over -1 would be -1. So these low points on the sine graph will also appear on the graph of the cosecant. And so using the points that we have here and the vertical asymptotes, I'll go through each point and approach the vertical asymptotes like so. Nice smooth curves. All right. So really what this means is if you're graphing the secant or the cosecant, what you really need to know how to do is to graph the cosine or the sine function and just go from there. Just bounce off the sine or cosine function, which ever corresponds to what you're doing there. So this is the graph of the cosecant of x. And then we want to find an equation of a sine function from this following graph. Okay, so this is a nice test problem because it's really easy for us to sketch a graph for you, and then you can figure out what that graph is. So for this graph, the first thing I would look on here if I was doing a sine function, well, actually the first thing I might do is what do I want to end up with? So I would remind myself that what I want to end up with is some function sine of x is equal to a, which would be the amplitude, either the positive or the negative of the amplitude, a times the sine of omega x minus phi plus b, where b is our midline. And the first thing I go for when I'm finding these numbers that replace the a, omega, phi, and b is I'm going to look for that midline. So right here, if you just look the high points, the low points on your graph, right in the middle is going to be right here. And this would be y equals 2. But what that actually tells me is that the number b that we're looking for here is going to be 2. So we'll start by finding the midline. From that midline then, it's fairly easy to figure out what a is here. So actually, I take that back. Let's go from finding the midline b. Let's find what phi is. Okay, so if I think of what the sine graph looks like, and if I'm starting, say this is the y-axis, this is the x-axis, usually the sine graph, let me fix that a little. Let's actually just redraw what I was trying to do there. Okay, so if I have my x and y axis, if I'm graphing the fundamental cycle of the sine graph, it starts here at the intersection of the x and y axis. It goes up, down, and then up again until we get to 2 pi. Okay, so let's look at the graph we have here. So if I start here on on the y-axis, where the y-axis meets my midline, notice I don't go up as I go to the right, I actually go down. And so if I wanted to look at what phi was here, notice that we actually could use this graph that we have. We could use the direction that the sine function takes, leaving the y-axis and going to the right, as long as we flip this graph about the midline. I hope that makes sense. But so just imagine this whole graph flipped about the midline, and then we would start where the midline meets the x-axis, or meets the y-axis, and we would go actually down instead of up. So that tells me that my amplitude here, how far do we go from the midline to get to a high point on the graph? We go 1, 2, 3 units. We could also find the midline, or find the amplitude by how far do we go down to the low point on the graph. Our amplitude is 3, but our actual value of A is going to be -3, because we would have to flip this graph in order to start off from the intersection of the midline with the y-axis, and to go down, we'd be taking a negative value of A there. So A equals -3. The other things we need to find are, actually, we just found the phase shift here, or phi, would be equal to 0, because we're starting off from the y-axis. We don't have to shift things left or right as long as we do some flipping about that line y equals 2. And so what are we left with finding? We're finding still the period. So the period, to find the period on this, I'd say probably it's easier to start here on our graph and go through a full cycle. So from this point at -2 pi, we go up, we go down, we go all the way down, we go up again until we meet our midline again. We've gone a distance from -2 pi to 2 pi. So our period here is 4 pi. And what I happen to know, if I'm trying to figure out what omega is here, then I happen to know that if I took 2 pi, divide 2 pi by omega, I would get 4 pi. That tells me that 2 pi equals 4 pi times omega. We can divide through by, we can pull out pi, divide both sides by pi, and we'd be left with 2 equals 4 omega, so that's going to end up giving me omega equals 1/2 here. Okay, so I think we have everything we need. We have omega, we have, why did I write phi equals 3? Sometimes it's hard to talk and write at the same time. It should be 0, right? Okay, so phi should be 0 because we don't move to the left or right from our original fundamental cycle. Okay, so we finish with S of x equals, remember A was -3, and then we have the sine of omega was 1/2, so we have -3 sine of 1/2 x minus 0, which was phi, and then B was 2 up here, so plus 2, and we have our transformation here of the sine function. -3 sine 1/2 x minus 0 plus 2. Okay, moving on. Sketch the angle theta equals -3 pi fourths and find two coterminal angles. Okay, so for -3 pi fourths, we're going to start on the x-axis and we're going to go clockwise since this is negative. And we go around here to this angle, through this angle, -3 pi fourths. This is how you'd want to write, if you were drawing this on an exam, you would put your ray, your terminal ray here, and you would sketch your angle with an arrow on it to point which direction you're going from the positive x-axis, and then I would also label your angle as, in this case, -3 pi over 4. So the other thing we're asked to do here is to find two coterminal angles. So to find the first coterminal angle, well, let's take negative 3 pi over 4. And then if we go a positive 2 pi radians from the negative 3 pi over 4, we would have the angle of negative 3 pi fourths plus 8 pi over 4. And we would simplify to write that as 5 pi over 4. So one coterminal angle would be 5 pi over 4. Another coterminal angle, we would take negative 3 pi over 4 minus 2 pi. That would be the same as negative 3 pi fourths minus 8 pi over 4. And we would call that negative 11 pi over 4. Of course, there's an infinite number of coterminal angles, and you could here choose any of those since there aren't any more specific instructions given. Okay, let's go on. We have a yo-yo here. A yo-yo with a radius of 1.125 inches spins at a rate of, so here's our yo-yo. We have a radius of 1.125 inches. This yo-yo spins at a rate of 4,500 revolutions per minute. And we want to know how fast is the edge of the yo-yo spinning in miles per hour. Okay, so the first thing I'm going to do, if I take a point on the edge of this yo-yo, how far does this point travel in one revolution? So the edge of the a point on the edge of the yo-yo in one revolution, the point would travel through a distance of the circumference of the circle, which would be 2 pi r. We see that r is equal to 1.125 inches, so we're going to have 2 pi times 1.125 inches. And so we'll just call the distance that our point travels in one revolution 2.25 inches. Okay, so if we travel, oh, I forgot the pi there. Whoops. Good to catch that now. In fact, that's a common mistake on these exams to forget to include pi in your final answer. So make sure you put pi there. So 2.25 pi inches. So what we want to know is how fast is the edge of the yo-yo spinning in miles per hour. So what else do we know here? We know that we go 4,500 revolutions per minute. So if we have 4,500 revolutions per minute, how far do we go then in 4,500 revolutions per minute? Well, in one revolution, we just found that we're going to go 2.25 pi inches in one revolution. Okay, so what we're doing here is we're multiplying by fractions that enable us to cancel out units and move on to new units. So we've taken care of the revolutions, and we'll take care of units as we move along. Let's start with, maybe since I see inches right here, let's go ahead and change those inches into miles. The way I change inches into miles is I start by changing inches into feet. So remember, 1 foot has 12 inches in it. And so we've changed inches to feet. And now I want to go ahead and change feet to miles. And usually you would be given this on an exam. 1 mile contains 5,280 feet. Okay, so at this point now we have changed our original inches into miles. So we can cross out the feet here as well. But we need to take care of one other thing. So we're looking at hours instead of minutes. Well, that's fairly easy to resolve. We're going to make note that there are 60 minutes in 1 hour. And so I can go ahead then and cross out the minutes, and I'm left with miles per hour, which is what we want. What we have left to do, though, is to plug all this into a calculator. The way that I would plug it into a calculator is I would take 4,500 times 2.25 pi times 60, and then I would divide by 12. I would divide by 5,280, and if we do that, we're going to get 30 on a calculator. You get 30.12180,456, and this is where, and it would keep going. This isn't an exact number. This right here is an approximate number, what it shows on your calculator. This is where you need to be really careful when you're taking an exam. If it says to round to 2 decimal places, do it correctly, or it will mark you wrong on this exam. So we want to round this to 30.12, and this would be miles per hour. Okay, so that's how fast a point on the edge of the yo-yo is spinning. Okay, let's go on. And here we have a problem that we did earlier in the semester. A 1,000-foot long wire is attached to the top of a tower. When pulled taut, it makes a 43-degree angle with the ground. How tall is the tower? How far away from the base of the tower does the wire hit the ground? Round your answer to the nearest tenth. So, okay, so we have, here's our ground, here's our tower, here's our wire. So the wire is 1,000 feet long. It's attached to the top of the tower. When pulled taut, it makes a 43-degree angle with the ground. How tall is the tower? We'll call that h for height. And how far away from the base of the tower does the wire hit the ground? We'll call that our distance. And then we're going to round to the nearest tenth. Okay, so what have we got going on here? We've got, let's find, what do we want to find first? Let's find maybe the height first. So to find the height, we have a right triangle here. And looking at that 43-degree angle, we need a trigonometric function that uses the opposite and the hypotenuse. So that would be the sine. So the sine of 43 degrees is going to be equal to h over 1,000. If I multiply both sides by 1,000, I get 1,000 times the sine of 43 degrees equals h. And so if I plug in my calculator, it's going to say h equals, and I need to take a quick peek here, h equals 681.998 3601 ... It would keep on going. This is as far as my calculator goes. And we need to double check, round to the nearest tenth. That means I need to round this 9 either up or down, or I need to keep it, or I need to go up. So basically the number next to 9 is another 9, so I need to move that 9 up. So to move that 9 up, it would make it a 10, which would actually leave a 0 here and put a 1 in the, with a 1. So it would, with the 681 would become 682. So we're going to say our height here is approximately equal to 682. If you want to, you can put 0.0 here, and that would be feet. Okay, this would be the approximate height. Then for the distance from the base of the tower, we look at the 43 degrees. We have adjacent and hypotenuse that we're working with here. That would give us the cosine function. So the cosine of 43 degrees is going to equal d over 1,000. Multiplying through by 1,000, we get 1,000 times the cosine of 43 degrees equals d. By the way, make sure your calculator is in degrees. When I tried this just a minute ago, I had my calculator in radians, and it will give you some really weird answers. In fact, if you do get weird answers when you're taking an exam, go back and make sure that you're in the right mode, either degrees or radians. So here on your calculator, you would get that the distance here is equal to 731.998 0.3537016, and we would round that to the nearest tenth, which would be the distance is approximately equal to 731.3. If there's a 5 to the right of the 3, I'm going to round up. So I'm going to write this as 731.4 feet. Okay, so there we go. One thing that I wanted to remind you of is when you're taking the exam, there's a few word problems on this, I believe. The angle of inclination. Remember, if your line of sight, if you're looking straight ahead, here's your eye, you're looking straight ahead here, the angle of inclination is going to go up, inclined. If we're looking instead at an angle of depression, then from your line of sight straight ahead, you're going to be going down. Your angle goes down from the straight ahead line of sight. Okay, so just keep that in mind when you're taking the exam. Past that, I think you'll be good. And if you have any questions before the exam, just make sure to send me a quick message and I'll get back to you as soon as possible.